Hi everyone, welcome. My name is Mohammed Al-Dali and I'm doing data science on my own. I'm going to share my experience with Code Alpha, and big thanks to Code Alpha for allowing me to participate in their internship program about data science. So this is my third and final video. I made the previous videos about the first two tasks I have been assigned with, and in this third video I'm going to go through the cars dataset. So I'm going to do some experimental data analysis and plot some visualizations to derive insights from our data. And then I'm going to build some models where I'm going to train them on some experimental variables to predict the target variable sending time. So let's get started. Bismillah. So first of all, we're going to import packages. So we import pandas, numpy for data manipulation, matplotlib, and seaborn for visualizations, and other models for the regression and so for predicting data, primarily scikit-learn. Then we start by importing our dataset and store it in the cars variable, and here's the head of the dataset. We got the car name variable, the year column, selling price, present price, driven kilometers, fuel type, selling type, transmission, and owner, and we're going to use them for predicting the selling price column. So here's some information about our data. We can see that there are 301 entries and 1 rows in our data set, and there are no missing values, and we can see that the data types are well assigned. So here we're going to check for any duplicate rows, and we can see that there are 2 rows that are duplicated entirely, so we can just draw the duplicates, and now we can see that there are no duplicate rows after all. Then we can use the describe method, so we can see how the numerical columns to see some statistics about them. So for example, the mean selling price is 4.58, present price mean is 7.54, and so on. We can see also the standard deviation, minimum, different percentiles, the median, and the maximum statistics in our dataset. And here's the pair plot, where we can see how the variables are correlated together, and we can see the distribution of each variable on the diagonal axis. So some variables don't show like real correlation, and we can see that most of the distributions are skewed. So later on, where we're going to build the models, we're going to use log transformation, because models can be better built when the data follow some assumptions and follow some good distribution of the models. So here's a heat map for the correlation between variables, and we can see that the selling price is highly positively correlated with the present price. So we can say for sure that the present price is a good predicting feature for the present price. The other features don't have similar high correlation between them. So here we're going to start to see how our data is distributed. So here is a histogram with a KDE plot for the distribution of our data, and here's also a box plot that shows the distribution. So here's the year. Mainly the year is between 2012 and 2016, and data is skewed. We can also see the selling price, which is totally skewed, and many of the selling price values are between like 1 and 6. Here's all the present price histogram and the box plot, and here's also for the driven kilometers, and here's also for the owner. So we can see that many of them are skewed, so we're going to use log transformation so we can make them look more like normal distribution, so the models will be better trained on these features. So what about the categorical variables like fuel type and transmission? So here I plot how the frequency, so the count of each categorical variable, and here I plot also how the selling price is different based on the categorical variable that we got. So for fuel type, we can see that most of the cars use petrol. However, the petrol is contributing less to the selling price compared to the diesel type. So diesel cars have higher price. Here's for the frequency of the transmission. So we got the dealer, the selling type. So the dealers are more than the individuals, and the dealers have higher selling price. Also for transmission type, though most of the cars are manual, but the automatic cars have higher selling price. So here I plotted also the top 10 cars by mean selling price. So I can see that Land Cruiser have the largest selling price with 35, then we got the Fortuner with around 17, and so and there are also other cars in our dataset, but here's the top 10 cars. So after I've done some visualizations and after I've seen that the categorical variables don't show like the same distribution between them for the selling price, so this suggests that selling price is different between categories, and so categories have different correlation to the selling price. So to be able to say that this difference is significant, we're going to use some non-parametric test to with a certain significance level to see if this information is significantly true. And the reason why I'm using the non-parametric test and not just parametric test like the t-test and so is because the data is not normally distributed. So here I built a significance function that do some non-parametric tests based on the data itself, and then we compute the p-value and we compare it with the alpha to see if the significance level is high enough to consider the difference. So we can see that the p-value is too low for the different categorical variables, which means that there's actually a significant difference in the mean of different categories when we are studying the selling price. And so we can conclude that the selling price depends on the category of each categorical variables. So preparing for running models, we first start by creating dummy variables. Dummy variables are like when we're assigning the different categories into 0 and 1 and 2 and 3 and 3 and so called, so the model can train on them, because the model can train on like strings and so. So here we got the dummies, and here I transformed the driven kilometer, the selling price and present price columns by log transformation to get better results. And here I stored the x variable, which contains the features in our dataset, and here I stored the target variable selling price with the log transformation. So before running the models, I did a lasso test which shows us how important the features are. So as we can see, and as we have seen before, the present price showed the highest correlation, and here we can also see that the present price has like 80% correlation with the selling price. So this means that the most important feature is present price with the log transformation for predicting our target variable feature. We can also see that fuel type diesel and has good correlation, and the selling type individual has negative correlation. The other values like have smaller coefficients, so they're not really contributing to the explanation of our target variable. So here we can see that in a more elaborated heat map correlation. So present price with the log transformation has the highest correlation. We can also see 0.5 correlation with selling price when the variable is fuel type diesel, and then we can also see that selling type individual has high negative correlation, negative 0.28, 82 with selling price log. So we can say that these explanatory variables are the most indicative of the target variable selling price. So the models are going to rely on them more and more. So we start with the common linear regression model. And so what we're going to do is to not just build the model, we're going to tune the model if it needs tuning for its hyperparameters, and we're going to build the model based on a cross-validation. So we can say that the model trains well on different sets of our data and generalizes well to different sets of unseen data. So we first split our data into training sets and a test set with 20% size for the test set to say that it generalizes well to unseen data, and we set a random state seed to make sure that the data is reproducible. After running cross-validation, we can get some results for the training R2 score, which shows how the explanatory data are explaining the seen data, and we can see the mean square error, which shows us how is the error between the data that we got and the actual data. So the results are pretty high. We got like 97%, 95% respectively for training and test R2 scores, and a low MSE for training and tests data. So here's the results of our cross-validation plotted into a visualization. So of course for the training it's going to be with less distribution, because the model is for sure going to work better on training data than the test data, the unseen data. So anyway, we can see that it still has above 93% R2 score, and the highest MSE is around 0.25. So it's still going pretty well. So one step that we can go further is by applying the ridge regularization, which is a good way of tuning the coefficients in the linear regression model. So ridge regularization usually gives us better results than the normal linear regression model. So here are the results with the MSE and R2 score. Then we built the key neighbors regressor model, which works based on the neighboring data to predict the data that we got. And I first want to tune the hyperparameters, majorly the number of neighbors, to see whether the model works the best. So as we can see here, at number of neighbors equal to 3, it has the highest R2 score, and also a low MSE with relatively low MSE and the training and test set. So we can choose k equal 3 for the KNN regressor. So here we initialize and fit the model, and here are the results for the k neighbor regressor with the 3 neighboring data. Then I built the decision tree regressor, and I tuned the hyperparameters and selected the best performing tree regressor using grid search CV by tuning here some hyperparameters like max depth and the minimal samples split and sample sleeve. And here are the best parameters that we got, and here are the results of the decision tree regressor with the best hyperparameters. And finally, I built the random forest regressor, and similarly with the grid search CV, I used cross validation and hyperparameters tuning to search for the best random forest regressor. And here are the best parameters, and here are the results of the random forest regressor. So I didn't went enough into the results because I prepared visualization where I can compare between the training MSE, the test MSE, the R2 score, and between the training and test data for all of our models. So as we can see, a lower training MSE is the best, and a higher R2 score is the best also. So we can see that the random forest, here colored in purple, has lowered MSE both on the training and on the test data, while the KNN regressor has the highest MSE and the highest on the training and test data. So the random forest is the best performer based on the data that we got on the MSE metrics, while KNN is the least performing one. Now, comparing with the R2 score, we can also see that the random forest regressor is performing the best both on the training and test data, along with the decision tree regressor. Also, KNN is still the one with the lowest R2 score, so it's the least one performing. So we can conclude that the random forest regressor is the best model we can build for predicting our data and to get the best predictions for the selling price target variable. So I hope I made things clear and pretty well explained and concise, and I hope you enjoyed me with the 3 videos, and thank you everyone for watching me.